Hi friends, welcome to my another video. Today in this video I will discuss about the disadvantage of poor power factor. This is part 4 video in series of capacitor bank sizing. Before this video I already discussed many things related to capacitor bank, like what is capacitor bank, what is the importance of capacitor bank in the electrical network, what are the different components of capacitor bank, how to calculate the individual rating of all components of capacitor bank, how to do the stepping for the capacitor bank. In this video we will cover what is the disadvantage of poor power factor. This video also will cover what is the significance of capacitor bank in the electrical system. Why? Because who is improving the poor power factor in the electrical network? It is nothing but capacitor bank. So when we will understand what are the disadvantage of poor power factor, we will also come to know the significance of capacitor bank in the electrical network. So let's start this video. Here I listed out some of the disadvantage of poor power factor. First one is more apparent power required due to poor power factor. We need bigger cross section area of the cable due to poor power factor. We have more copper losses due to poor power factor, and due to poor power factor we have poor voltage regulation, and we have to pay more extra bill, more utility bill due to poor power factor. We will discuss each point in very detail. So let's start. The first point here I mentioned that we required more apparent power when there is a poor power factor. As we know that the apparent power is equal to active power divided by power factor. Suppose I have taken a project which having a total connected load of 1150 kilowatt. Okay, 1150 kilowatt here. Now what is the apparent power when the 1150 kilowatt load is connected at 0.8 power factor? Then the apparent power requirement is 1437.5 kVA. Now this is the power factor when we connected a load of 1150 kilowatt. Now I introduced a capacitor bank in the system which having a total connected load of 1150 kilowatt, same load. Okay, but I introduced the capacitor bank in the system, so the power factor improved from 0.8 to 0.9. In this case the apparent power requirement is just 1277.8 kilowatt. If you will compare the apparent power requirement at 0.8 and 0.9, you will observe that the apparent power requirement at improved power factor is lesser than the apparent power requirement at the poor power factor case. So how much we are reducing when we are improving the power factor from 0.8 to 0.9? It is 159.2 kVA apparent power requirement we are reducing with the improvement of power factor from 0.8 to 0.9 at the same load in both the cases, that is 1150 kilowatt. Hope you are clear now. Now let us move to the other point, bigger cross section area. As we know, P is equal to root 3 into V into I into cos phi. So I rearrange this formula. I is equal to P into 1000 by root 3 into V into cos phi. Okay. At 0.8 power factor, we got the current value of 2174.91 ampere. Okay. And I introduced the capacitor bank now in the system, so the power factor improved from 0.8 to 0.9. I took the same example in all the cases. Okay, so the current requirement in the system is now 1844.36 ampere. So what we observe in both the cases, that when the power factor is poor, the current requirement in the system is more, and when we improve the power factor from 0.8 to 0.9, the requirement of current is reduced. So as the current requirement is reduced, so the cable which is carrying this current, as the current reduced, so the cross section area of the conductor also required less. Why? Because we reduce the current in the system. Our load is same in both the cases, 1150 kilowatt, but due to improvement of the power factor, we reduce the current. In order to carry this reduced current, we need a reduced cross section area of the cable. It's very simple, right? So due to poor power factor, we have to use bigger cross section area of the conductor or cable. Now let us move to the other point. More copper losses. As in the previous case, we clearly seen that at 0.8 power factor we have 2174.91 ampere, and at 0.9 power factor we have a current requirement is 1844.36 ampere. It meaning at improved power factor we required less current. As there is a less current in the system, the copper losses will be also less. Why? Because the copper losses is proportional to I square R. So as the current reduce, the copper losses will reduce. Why the current is reducing? Because we improve the power factor. So with the poor power factor we have more current, so the copper losses will be also more, and with the improved power factor we have lesser current, so accordingly the copper losses will be less in the system. Hope you are clear with this point. Now let us move to the other point, that is poor voltage regulation. As we know that V is equal to IR. Here R I mentioned Z because Z is the impedance, that is equal to under root of R square into reactance square, Z square. But as from this relation we know that when the current of the system increase, the voltage drop also will increase, right? And we seen in the previous two cases that at 0.8 power factor we have more current requirement compared to 0.9. So at poor power factor the current requirement in the system is more, so the voltage drop in the system also will be more. Hope you are clear with this point. Now let us move to the other point, that is the extra utility charges. As we seen in the first case that for the total connected load of 1150 kilowatt at 0.8 power factor compared to 0.9 power factor, we are using more apparent power, that is 159.72 kVA apparent power. We are requiring more from the distribution company. So distribution company will charge this for this extra apparent power. Okay, so what we observe, suppose if in UAE the charges is 0.3 unit, so for this much apparent power we have to pay 47.9 dirham every hour. And suppose this load is running throughout the year for half of the year, then how much money we have to pay extra? We have to pay extra around 200,000 dirham per year, which is the huge money. So if we will improve the power factor from 0.8 to 0.9, then we can save this 200,000 money every year. So this is the big achievement. I hope you clearly understood what is the disadvantage of poor power factor. If you really like this video, then please give thumbs up and subscribe to my channel. Please share this video with your electrical friend. We will meet in any other video. Till then, take care, keep learning, and bye bye. Thank you so much.